For this section, derivative is a rate of change, I want to start us off by thinking back to what we did in our very first class, our very first online lesson. We talked about the idea of a limit. When we did that, we looked at a function, any function. Just for our purposes today, instead of f of x, I'm going to call this function s of t. All right, so this will be the t, and this is going to represent s sub t. So what we looked at on that very first day of class, on that first lesson, was first of all, we did what we called an average velocity. We called it VAV to correspond with the red line. And the average velocity, we said, well, wait a minute. The average velocity is just essentially the slope of the line, because the velocity is your change in position, and that, in essence, is your slope. So if we call this point here T1, T2, we have S of T1. We calculated average velocity, excuse me, by just looking at the slope. So change in what would be our y-axis, which is our S of t. So S of t2 minus S of t1 over change in x, which is our t, t2 minus t1. And that was our formula for average velocity. So on that first day of class, that first lesson, we kind of talked about taking this point right here, the t sub 2 comma s sub t sub 2 point, and moving it so it got closer and closer to our initial point. And as we did that, we calculated these average velocities as they got closer and closer. Because what we really wanted at that point was the initial velocity, instantaneous, sorry, not initial, instantaneous velocity at t sub 1. In other words, we needed the slope of the line tangent, not the secant line that goes through t sub 1 and t sub 2, but we wanted the tangent line that was right at t sub 1. Well, since we only had the one point, we couldn't calculate the slope of that particular line if we tried to use the average velocity formula. Obviously, we got 0 in the denominator. So, very first lesson, we used limit. The idea of the limit. Didn't quite get into limit yet, but we just said, well, let's calculate as it gets closer and closer, and we were able to determine, to infer what it would be. Then, fast forward to the beginning of Chapter 3, to the very first lesson in Chapter 3, we talked about the limit definition of the derivative. And the limit definition of the derivative says, well, wait a minute, we can get the derivative, which is essentially the slope of the line that is tangent at a point, by taking a limit. And ultimately, that would become, if we kind of put those two lessons together, we can indeed find the instantaneous velocity by applying the limit formula, the limit definition for the derivative. So I'm going to make a couple of adjustments, because we know that formula is f of x plus h minus f of x over h. Well, I want to adjust it to what I have written here. When we can see that I'm not going to use h anymore. What I'm going to use is the change in time. So time 1 to time 2 represents a change in time. So I'm going to represent that as delta t. Delta is the standard formula for change. Well, if I call that delta t, I still have t1. And then this becomes, we don't, in fact, because we only have t1, we don't even have to call it t sub 1. We'll just call it t. T plus delta t. And then over here, I would change this to simply s sub t. And then I would change this for my tangent line in blue to s of t plus delta t. From there, I can certainly apply my limit definition and say, okay, it is going to be s of t plus delta t, it's my second position, minus the first. And if you think about it, t minus t plus delta t minus t, if you do all that, you are going to end up with simply delta t. As delta t, because that is my new h, goes to 0. So this essentially is my instantaneous velocity. In other words, instantaneous velocity is simply the slope of the tangent line at a particular time, meaning it's a derivative of position. So how do we show that? Well, if s sub t, let me do this in black, if s of t is our position function, and s of t is a standard notation for just position of a particle, position of an object, position of anything at a particular time. It's kind of a standard notation. You'll see it here. You'll probably see it in physics as well. And then what we just discovered that the velocity, and when we talk about velocity from this point on, we're not doing average, we are doing instantaneous velocity. So we're just, all velocity is going to be instantaneous. So v sub t is simply, oh wait, I can get that by taking the derivative of the s sub t function, and that is my velocity function. So the velocity function gives you the velocity of a particle at a particular time. Position function gives you the position of the particle, sometimes represented by height. You have to read the problem to determine that, at a particular time. And then finally, if you think through this, you know, velocity is change in position, right? The rate of change of position. Ask yourself, what is the rate of change of velocity? Well, the rate of change is velocity we know as acceleration. So you'd repeat this process. Acceleration is the derivative of the velocity function. But we could take that one step further and say it is the second derivative of the position function. And this is acceleration function. Because acceleration is the rate of change of velocity, and it's the second rate of change of position. So essentially, this is what we want to kind of get out of our 3.6. It's an idea that you will revisit at the very beginning of Calc 2, when you, after you've gone through the introduction to integration, where you kind of go backwards from derivatives. All right. So based on this particular rate of change, we are going to go through two examples in this video. And then I'm going to take this idea and relate it to business. And we're going to go through a rate of change problem, not with velocity, obviously. That one's going to be based off cost for a business application. So we have three applications I want to look at. All right, number one. So we've got this idea down. All right, and this is the idea we're going to use to solve these problems. All right, so the first problem, example 1. Sorry about that, let me switch that. Position of a particle. So this is more about theoretical position, but the idea is we're just going to look at a particle moving along a line. Nothing. So what do I mean with that? We have a line. We have this particle. We have a starting position, initial position. It goes. Maybe it goes back. Then it turns this way. Then it goes that way. All right. So we have a particle kind of just zooming back and forth across the line. All right. That's how I want you to picture the particular problem we're doing now. Again, this one's a little bit more theoretical. The second one will be a little more applicable, something you're a little more familiar with. Okay, let's suppose that the position of this particular particle, the position function of this particular particle, is 2t cubed minus 21t squared plus 60t. All right. Well, and we're going to just limit our time, in other words, limit our domain, because time is our x in this particular problem. I'm going to say, we're going to just do it for values between 0 and 6 seconds. These are in seconds, of course. 0 seconds and 6 seconds. All right, so since we're going to be doing and asking a lot of questions, one helpful thing at this point might be to say, okay, if that's the position function of this particular particle, what is the velocity function? So we might as well go ahead and find that. All we need to do is take the derivative of the position. So think about that for a second. Hit pause if you need to, if you want to work it out first on your own. That's going to give us 6t squared minus 42t plus 60. There's our velocity function. And, you know, depending on the questions we get asked, we might need acceleration. So let's go ahead and find that. Acceleration, of course, the derivative of the velocity function. So 12t minus 42. So we have our three functions. Now here's the tricky part. Based on the question being asked, you need to figure out which function you're working with. So here's my first question. Hey, when is the function stationary? Well, when is it not moving? Well, clearly it's not moving at time 0 because it needs to start, right? And since we're only going to 6, it's not moving at time 6. So we've got 0 and 6. Think about what happens if a particle were to stop moving. The position for a moment stays stationary. But we don't know what that position is at any given time. So it's not the position we're necessarily concerned about to determine when a particle is stationary. When something is stationary, position is not changing, which means the velocity has to be 0. So when is a function stationary? When is our particle function? Our particle, I called it the function. When is our particle stationary? When v sub t equals 0. All right. So if you can figure out when v sub t equals 0, and again, I wrote function, I apologize. I really meant to say particle. It's the idea. When v sub t equals 0, that is when your particle is going to be stationary. So we got to just take we've already found v sub t. All right. You have to solve this. This happens to be a quadratic now. You got to solve it. So let's factor out our 6. You can cancel it away. T squared minus 7t plus 10, I can then factor further into t minus 5. And we found it equals 0 at 2 seconds and 5 seconds. So let's think about that for a minute. Let's draw it. Always draw pictures. It helps you to determine what's going on. You know, our particle's starting at 0. We know it does something where it becomes stationary at 2 seconds, then at 5 seconds, and we only care about what happens up to 6 seconds, because that's our domain, essentially, for time. So over time, here's what we have. Now what we need to determine is for the second follow-up to this question, so this is when it's stationary, 2 seconds, 5 seconds, and of course 0 seconds, and 6 seconds just by the domain. So the follow-up is, hey, when is the particle moving forward or backward? So the particle stops and essentially then goes in the other direction. So you need to determine what's happening within these time intervals. In other words, hey, what is going on with my particle between 0 and 2 seconds? So this, you can also look at velocity. Velocity is going to be positive when it's moving forward and negative when it's moving backwards. So between 0 and 2, if you were to plug in, this is, you kind of looked at this, you used to do these intervals, these quadratics in intermediate algebra classes, where you looked at, well, what's happening to my function between those values? Is it positive or negative? The good news is it'll remain the same between 0 and 2. So all you really need to do is think about, okay, if I take the number, for example, 1, and plug it into t minus 5, t minus 2, am I going to get a negative or positive value? So, well, if I plugged in 1 minus 5 is negative, 1 minus 2 is negative. What's negative times negative? Positive. You get a positive, which means your particle is moving forward. Okay, and it's going to move forward for that whole thing. Then what happens? It comes to a stop. The velocity goes to 0. The only way you can do that is because it's going in the other direction. So what's happening between 2 and 5? Try it. Plug in 4. 4 minus 5, that's a negative, but 4 minus 2 is a positive. So negative times positive is going to give you negative. It's going backwards. All right? And you're just going to continue that for all the intervals you have. We only have one more interval. Between 5 and 6, clearly if you plug in a number larger than 5, you're going to get positive, positive, positive. So here's what we know. On the interval 0 to 2, my particle's moving forward. On the interval 2 to 5, my particle's moving backward. And on the interval 5 to 6, it is moving forward again. So this will set us up for our next set of questions. And our next set of questions are, what is the displacement? I'm going to put in parentheses for that net distance. And total distance of the particle. Okay, so let's talk displacement for a minute. Displacement is the difference from where you began to where you ended. Displacement doesn't care what you did in between to get there. In other words, if you live a block from school and you drove to school and it was only 1 block, your displacement is 1 block. But in driving to school, if you stopped at the bank, stopped a quick check to get some lunch, made a bunch of stops, your displacement is still 1 block because you ended up at school, which is only a block from your house. Now your total distance, of course, that you drove is much greater. But right now we're just going to look at displacement. So displacement refers to distance, which refers to position. We need to use our position functions to talk about distance. In other words, hey, what is the position at 0? What was my initial position? So you have to go back. You should have it on your paper. I'll scroll up for a second. And clearly look at your position function, which is the 2t cubed minus 21t squared plus 60t, and plug in 0, and you can see right away if you plug into 0 that you're just going to get 0 because everything's going to cancel away. All right. Now, find end. I'm ending at 6 seconds. Well, now I want to plug in 6, right? So I need 2 6 cubed minus 21 6 squared plus 60 times 6. And if you do all that work correctly, you can stop and do it yourself. It's going to be 36. So my displacement and I didn't give a measurement for this, so let's suppose our particle is just moving, let's suppose S sub t is in centimeters. Doesn't matter. So then it would be 36 centimeters over those 6 seconds. That's displacement. But we know that, wait a minute, our particle moved forward for 2 seconds, then it moved backwards for 3, and then it moved forward for another second. And while it might have ended up 36 centimeters from the beginning, it moved a lot more within those intervals. So knowing when your particle stopped is going to help you get total distance. Because think about it. And this is why I wrote this little chart, 0 to 2 moved forward, 2 to 5 interval moved backward. We're going to use that to calculate our total distance. So basically you have to find the distance with an h interval. So let's take a look. From 0 to 2, again, we're using position function. And here's the next step. You would take, well, let's say, S sub 2, position at time 2 minus position at time 0. Here's the thing though. We talk about distance, it's always a positive. It doesn't matter moving forward or backward. It's going to be a positive distance. So at the end of the day, you got to make sure you take the absolute value of those. So S sub 2 minus S sub 0. Well, we have S sub 0. So what we need to do, obviously, is calculate S sub 2. If you go ahead and plug into, for time's sake, I'm just going to write the answer. You can calculate it on your own. It ends up being 52. You can see we will also need an S sub 5, position at time 5, and that is going to be 25. So these values you can calculate the same way we calculated number 6. So this one is going to end up being basically the absolute value of 252 minus 0, and that's 52. So in those first 2 seconds, it went really far. Then it went backwards for 3 seconds. How far backward did it go? Well, you'd have to take S sub 5 minus S sub 2. And S sub 5 is 25 minus 52. And you get absolute value of negative 27. So you get 27 and actually move 27 centimeters. And then between 5 and 6, you'd have to take S sub 6 minus S sub 5. And that, of course, is going to give you S sub 6 was 36 minus S sub 5, 25. And 36 minus 25 is 11. So my total distance was 90 centimeters. Right? Much larger than our displacement. All right. And then finally, you can be asked a question about acceleration. Hey, what is the particle's acceleration at t equaling 3 seconds? Well, for that, you need your a sub t formula. And find it at exactly 3. And acceleration is negative 6. And acceleration is actually centimeters squared over s. And there's your acceleration. Okay. Now, let's go back to a problem you're a little more familiar with. And that has to do with projectile motion, or we call motion in a gravitational field. So you know this is projectile motion. You've done these problems probably in high school, in your algebra class, possibly in a pre-calculus class. It's the one where you shoot a rocket in the sky. It follows a parabolic path because it has a quadratic as its function. These always have a quadratic as its function. There's like a standard... We'll still use S sub t because we're talking about position. Sometimes it's H sub t for height, but there is a standard formula. It was, you don't need to know this formula. It was like -1/2 g t squared plus v sub o t plus h sub o. So what you'll often see is -1/2 times the gravity, v sub o representing your initial velocity, and h sub o representing your initial height. T, of course, is time, and s sub t is the position. So, again, you don't need to know that now. You'll probably need to know that when you get into analytical physics next semester, but for now, you'll be given a standard function. So for this problem, let's use the function -16 t squared plus 64 t plus 96. And that gravity number is really going to be based on what measurement you're working on. This particular problem is going to be in feet per second. All right, just to make it easy, we're going to do this one in feet per second. So that's where the -16 comes from. All right. So we have initial velocity of 64, 60, and what we're representing is a stone that is thrown from a bridge into a river. So this represents a stone thrown from a bridge to a river. Okay? That's what we got going on. So we can ask a couple questions related to that, but before we get started, let's go ahead and again find our velocity function and our acceleration function because we will need them through solving these problems. So our velocity function is -16 t squared. Sorry, just started copying instead of thinking. -32 t plus 64. And what happens with any projectile motion? Acceleration is actually a constant. Once gravity acts on it, velocity actually changes at a constant rate. So acceleration itself is a constant. And in this case, it's just -32. So there's a lot of different questions you can be asked, and like I said, you have actually done problems like this before, and I'll kind of go over that a little bit. But first, here's my question. What is the highest point above the river reached by the stone? So I know I didn't put the full problem down, but the idea is you're throwing a stone up and then it falls from the bridge, you're throwing it up into the river. So, you know, you've got the bridge, the river's down here, the stone is going up. It's going to hit and then it's going to come down. All right, so we want to know the highest point that that stone actually gets to. All right, well, couple things. If you think back to the last problem we just did, when that stone goes up, right, it's going to hit a point where then it has to fall down. When it hits that point, before it falls down, it comes to a stop. That is a clue for you to start with your velocity function and go back to what we did before. Well, wait a minute. When v sub t equals 0, that is when our stone stops in the air, because the velocity has to hit 0 before it turns around and falls back to the earth. So if we can find v sub t equaling 0, we can get on the right track. In other words, we'll have the time. This will give us the time the stone reaches highest height, or it's at its highest, whatever. The stone reaches the highest value. So let v sub t, which is negative 32, so that means 32t equals 64t equals 2. Oh, it's only 2 seconds. In 2 seconds, that stone's going to reach its highest, the highest it'll go. Question wants to know, what is the actual height? Well, now that you know the time is at 2 seconds, you want the highest position. You need to go back to the position function to get s sub 2. S sub 2 is going to be our negative 16(2) squared plus 64(2) plus 96. And if you do all that math, I believe you get 160 feet. Yeah, you get 160 feet. So I want to stop you for 1 second, and I want you to take a minute, think back to when you worked on parabolas, because it's not that the path of the stone itself is parabolic, but, and I'm going to do this in blue over here, but when you look at this time related to the stone's height, or s sub t in this case, all right, at time 0, we're standing here on a bridge. The stone goes up, goes up, goes up, hits the highest point, comes down, comes down, comes down, and hits the ground. Okay, so that's why we say it becomes a parabola. You learned how to find what we call the vertex of a parabola. Sorry about that. There we go. Does anybody remember how to find the vertex of a parabola? Oh, the vertex of a parabola, you start is negative b over 2a, and then the function of negative b over 2a. Well, go back to your original position function. What's negative b? Well, b is 64, right? Here's our position function. S sub t equals negative 16 squared plus 64t plus 96. Negative b is negative 64 divided by 2a divided by negative 32, because negative 16 times 2. So negative b over 2a, just comes out to 2. So that negative b over 2a formula you used prior is because it came from the derivative of the function. All right? This just happens to be a quicker way to get it. And then, of course, you plug it in, you get your 160 feet. Okay, next question. With what velocity will the stone strike the river? With what velocity will the stone strike the river? So, remember, it's not necessarily velocity we're looking for right away. Everything goes back to time. If you can calculate what time the stone will strike the river, you can then plug it into the velocity function. So with what time will the stone strike the river? Well, if you go back to our graph here it is. Let me bring it back to the center of the screen. Goes up, goes up, goes up, goes up, goes up. Right here, I want this t value of the position function. In other words, I want the intercept of the position function. So read that. Oh, I want when S sub t equals 0. S sub t is negative 16t squared plus 64t plus 96. That is not factorable. In fact, you probably need to use a quadratic formula to solve that. So you can, and no, I'm not going to make you use a quadratic formula on the test. It will be something factorable, but you know what? When you're doing your math lab problems, you've got technology to help you with this. You can find a quadratic formula calculator and it'll give you your answers for t when that whole function equals 0. So you can use the quadratic formula or just use technology, AI. You know, when you're doing your homework, feel free. On the test, you will not be able to use that, but I will give you something you can factor. All right. So t actually comes out to negative 1.16 and 5.16. Well, clearly, I'm going to go back to my graph for a second. Yeah, the negative 1.16 is totally out of the domain of time, so we would not use that. But the 5.16 we are going to use. The stone's going to strike the river in 5.16 seconds. So all you need to do is figure out what is the velocity of 5.16. And if you go ahead and plug that into your velocity function, you can do that on your own. You get a velocity of negative 101.12. The stone's coming down, so it makes sense that it is negative. It's no longer going up. All right. So there's a way to use derivatives for a type of problem that you are familiar with. Okay, last one for those few business majors out there. In business, we have something called C of X. C of X is our cost function. And they are pretty crazy functions. It's basically the cost, total cost of producing X amount of products. It represents total cost of producing X products. So once you have a cost function, you can say, hey, what's the cost of making 100 products? What's the cost of making 1,000 products, just by plugging it in? All right, that is your basic cost function. Any X you plug in gives you the total cost of all the products up to that number. Usually with a cost function, making those first few products, like product number 1, is always the most expensive one to make, because when you take into account all the material you need and everything, obviously that cost goes down. So product 100 is going to be a lot less to produce than product 1. All right. But the cost of producing 100 items is going to be more than producing one item, because you got the cost of item 1 plus the cost of item 2 plus the cost of item 3 and so on and so on and so on. But what happens is each product you make, obviously the cost starts to go down a little bit. All right. So then we can get something what we call average cost from this cost function. So again, the first 100 items, every item costs, every time you make an item, it costs a little bit less, but there's an average over the whole thing. So the average cost is simply take your cost function and divide by X. And that is equal, we put a bar over C. If you taken any statistics courses, X bar represents average, so that bar should make sense to you. So C with a bar over it is your average cost function, and it's found by taking C of X divided by X. Now, for those of you that are in business, you are aware of something called a marginal. I can't spell. Marginal cost. A marginal cost is the cost of making the single next item. What is the cost of producing? So basically, it's the change in cost. Because as I said, each item you make, the cost goes down, just of that individual item goes down a little bit. Total cost goes up, but individual goes down. Excuse me for 1 second, I had to take a short break. So where were we? Marginal cost. So marginal cost, those of you, the business students, you're probably already aware of this, is just the cost of producing that next item. So in other words, the marginal cost when X equals 100 is the cost of just producing the 101st item. In other words, it is the rate of change of the cost. So because of that, marginal cost is the derivative of the cost function. And when you take the derivative of the cost function, you plug in a number of products for X, you get the cost of making that one next product. All right, so there are how your cost functions are related. Let's start with one quick example. As I stated, cost functions are a little crazy. So this one is negative 0.02 x squared plus 50x plus 100. And this covers products up to 1,000 products. So this cost function works from 0 to 1,000 products. So, well, let's find our other functions. C prime of x, or C bar of x, our average cost function is going to be the cost function divided by x. So in other words, you're going to divide each of those by x. So imagine each term, when you divide by x, x squared goes to x. 50x just goes to 50, and it becomes 100 over x. So that's our average cost function. Our marginal cost function is the derivative, not of the average, be careful. You want to take the derivative of the original cost function. So it's negative 0.04, because multiplied negative 0.02 times 2, x plus 50. All right? So there's a lot of different things that you can do to work with your functions here. So the first thing we want to find is, hey, suppose we have 100 items. What's the cost of 100 items? That'd be so all I did is plug in 100. This one I don't have calculated yet, so let me hit pause while we calculate. Okay, so I got that to come out to 4,900. So in other words, what does that mean? It cost $4,900 to produce the first 100, all 100. Of course, we can get the average cost by taking that cost function. Let's plug in 100. Or we can use our average cost function. So you can do this one of two ways. You can just go right to the function negative 0.02 times 100 plus 50 plus 100 over 100 by plugging in x. Or you can just take the 4,900, which you already found, divide by 100. Either way, you should get $49 per item. So that means up to the first 100 items, it was averaging $49 an item. Okay, only up to the first 100 items, averaging $49. So if you think about that, the cost to make the next item should be less than $49 because that was the average up to that point. And the cost to make each additional item is always going to go down very slightly. So C prime of 100 is negative 0.04 times 100 plus 50. And that comes out to, it comes out to about $46. I think it was something like $45.90 something. I just lost that on my calculator, but I'm going to put approximately $46. Okay, approximately $46. I think it was 45.9 something. So again, this right here, when you find the cost, that means the cost to produce the 101st item is about $46. Okay, that's what we mean by marginal cost. All right, so there's your rate of change video. And, you know, for the lab, this will certainly help you with some of those problems. And for the test, you will only really need to kind of do this type of problem here. The one where we look at a gravitational position of a particle, motion in a gravitational field, position of an object in a gravitational field. So you want to kind of look at that second example we did and think about that's more of what you will see on the exam. Where all of them are on the lab, that's the one you're going to look at on the exam.